Welcome back to my course Aspects of Biochemical Engineering. Now presently we are discussing very important topic, that is on enzymatic reaction kinetics. In last couple of lectures, I try to concentrate on what we mean by enzymes, how the activity of the enzymes can be expressed, and how the substrate and enzyme, they can interact with each other and give the product, and Michaelis-Menten equation just to find out the reaction kinetics, and how Biggs and Helden justified the Michaelis-Menten equation with the help of reaction kinetics. That now Michaelis-Menten actually that they propose the equation V equal to V max S by Km plus S on the basis of correlation between velocity of reaction and substrate concentration, and later on Biggs and Helden justified this with the help of reaction kinetics. Now, then we try to find out how the different constants, that Vmax and Km, can be estimated with the help of different plots like Lineweaver-Bach plot, Adie-Hupstein plot, and Henseul plot. Now, then we also discussed that how substrate and enzyme, they can interact with each other to give the product. There are different hypotheses, lock and key hypothesis, proximity effect, orientation effect. And then we developed the correlation, mathematical correlation between substrate concentration and time of reaction, just to find out that at what time we will get how much substrate will be converted. Then we also try to find out that different type of reactor we considered, like batch process, CSTR, continuous start tank reactor, or plug flow reactor, how the batch time or space time for the CSTR and the plug flow reactor can be determined. Also we discussed some problems, how this help you for determining the volume of the reactor, and on what basis you can tell that what should be the proper design for getting a desired amount of product. So this we covered in the last couple of lectures. Now today we are going to discuss a very important topic, that enzymes are very sensitive to the environment. So different physicochemical parameters plays very important role for on this enzymatic activities, and as physical parameters, when we consider, there are three different parameters we have. One is temperature, shear forces, and surface tension. Now when we talk about the chemical parameters, mostly we concentrate on pH, and the pH is nothing but concentration of hydrogen ion in the reaction mixture, and the concentration of different chemicals present in the reaction mixture. The first I want to discuss that that effect of physical parameters. Now, if you look at the physical parameters, we have temperature. We have temperature, then we have fluid forces, and also I told you the surface tension. Now, first let me give you that what is the effect of this temperature. Now, when we talk about temperature, the rate of reaction increases with temperature. Am I right? With up to certain limit. Now, question comes, with the increase of temperature, why the rate of reaction increases? That is the question. Now, if you look at the answer to this question is this, that I already mentioned that enzymes mostly they are protein in nature, and protein these proteins are mostly, they have the folded structure, and this folded structure is mostly due to the hydrogen bonding. Now, if you look at the strength of hydrogen bonding is very less, 3 to 7 kilocals. Here it is given here. You say 3 to 7 kilocals per mole, and but if you look at the deactivation energy of the enzyme is about 68 to 73 kilocals per mole. So it is quite high. So, now if you increase the temperature, that means you are putting some energy to this particular mixture. So, enzymes, a time will come that this force of attraction due to hydrogen bonding, that will be totally nullified, and when it is nullified, the enzyme will be unfolded, and when as soon as it is unfolded, the active site that is formed in the enzyme, that will be lost. As soon as the active site lost, then the enzyme will lose its activity. So, this is how temperature affect this activity of the enzyme. Now, question comes, the initial phase, if you look at here, if you the typical example, this is the enzymatic activity, this is the temperature. As the temperature increases, this slowly increases, then it fall very rapidly. When it is unfolded, then actually that the activity of the enzymes is fall very rapidly, because when the unfold, and this is irreversible in nature, this is not reversible in nature. So, this is the major constant. Now, question come, as you increase the temperature, why the enzymatic activity increases? The reason is, possible explanation to this is that since it is the hydrogen bonding and you are putting more energy, so as you increase the energy, you keep the heat energy. So, your active site will be just that it's about to unfold and fold, that kind of oscillation characteristics that will be built up, and with that characteristic, more substrate will be attracted to the active side and give the product. This is how the velocity of reaction increases with temperature. Now, the decrease, I explained that due to the denaturation of protein, how the decrease is taking place in this way. And now, during the activation period, this equation is the V equal to K into E, that is the velocity of reaction depends on the enzyme concentration. Now, this velocity of reaction is as per Arrhenius equation. This is the Arrhenius equation, A equal to e to the power E A by R T. Now, if you look at now, when you write the Arrhenius equation, K equal to A e to the power minus E A by R T, am I right? Now, the K we have already shown the K is equal to K into E. We have shown that. So, it is proportional to V, am I right? So, I can write ln K, or I can write ln V, this is equal to ln A minus E A by R T. I can write it like this. Now, if you plot that ln K or ln V versus 1 by T, so you will be having this kind of plot. So, if you when 1 by T decreases, that means T increases, your K value increases, or if you write ln V, velocity of reaction increases. But when it falls very sharp, because this will, if you are not here, I want to mention that we know that inorganic catalyst also that but there also at high temperature deactivation take place, but their deactivation nature is little bit different, like this. They are not sharp. Here in case of enzyme, this fall will be very sharp, but in case of inorganic catalyst like palladium, nickel, this fall will be little bit slow, that as compared to that of the reason is that in case of enzymatic reaction, the total unfold of the that protein molecule will take place, so that your enzyme will lose the total activities. Now, here if you take a slope here, what will be the slope? Slope will be equal to E A by R T. Am I right? So, R value is the gas constant. Now, if you put the value of R, you can easily find out the E A value. What is the E A value? E A value is nothing what is called activation energy. Activation energy. Okay. Now here, but we have at the same time we have another plot like this. So here if you take a slope, this slope will give you the deactivation energy ED. This is the what is the energy required for the deactivation of the protein molecule. That also we can calculate. So both the activation energy and deactivation energy can be calculated when we study the effect of temperature on the enzymatic reaction. Now, now here we have shown the similar type of plots that as I mentioned before, and so this is the equation that we have with the Arrhenius equation, and this is the this in this we can this will help you to find out the Kd value, that we can use the value, and from that we can find out the Ed value. This will Kd is that we if we consider dA, rate of deactivation of the cell, we can write dE by dt equal to Kd into E. Now if you so this if we write Kd equal to that, this equation is there, and from that we can find out the value of Ed. And here from this slope we can find out the EA, and this plot we can find out. I explained before also. Now next very interesting thing is the fluid force. Let me show you how we can explain that. Now suppose one liquid is passing through a pipeline like this. It is and all of a sudden you reduce the cross section area of the pipe. So what will happen? The velocity that we have here V, and this is V2. Now as soon as we reduce if your flow rate is constant, then what will happen? Your V2 will be much higher than V1. Am I right? So it will, the velocity increases drastically. Now as the velocity increases, then there will be some kind of shear forces, and due to shear forces, it so happens your active site of the enzyme that will be denatured. But this denatured is reversible in nature. But what I want to mean, that suppose again I put it in the higher diameter pipeline. So as long as they are present in this narrow pipe, they are under stress condition. As soon as we release the stress here, some of the activity, not 100% activity, some of the activity of the enzyme they will get back to the system. So that is why I call that this is the reversible in nature. In case of this is how shear force acts on this. So this is the enzymes. So here you see the enzymes are susceptible to the shear stresses during the production, isolation, and purification. So here I have taken the example of catalase and urease enzyme. What is the role of catalase? We know all the H2O2 that in presence of catalase it produces H2O plus oxygen. Am I right? And this mostly this catalase enzyme present in the aerobic organism, and obligatory anaerobic organism they don't have catalase enzyme. That is why the oxygen is detrimental for their growth of the organism. So here it has been found that this is what is called the shear rate into exposure time. Now as this is increases, now it is like this. So it is initially we don't have much of deactivation of enzyme, but if you keep on increasing this exposure time, then what will happen? The activity will decreases. And same thing happens in case of urease. What is the urease? Urease enzyme that acts on urea to liberate ammonia. So this decrease of the activity will take place. The hydrodynamic shear force causes the denaturation and inactivation. The loss of activity can be attributed the changes in the structure due to fluid shear. That is exactly I am saying, that is shear forces that will change the structure of the active site. That is why when substrate come, they will not get their proper sitting place at the active site. So your activity of the enzyme that will decrease. Now shear effect affects the efficiency of the enzyme recovery and final yield of the product. So this is in addition to that, another effect, the physical forces that we have, what we call surface tension. Now what is surface tension? Now when we know, when you talk about any kind of biological fermentation process, then the foam formation is a common characteristics of most of the fermentation process. Now due to formation of the foam, that there always will be interface between gas and liquid, and in between the gas and liquid interface, there is tremendous surface tension, H dynes per centimeter. That is usually we might be aware that the enzymes which secreted by the living cells, they usually having the surface tension about 1 dyne per centimeter, but here 80 dynes. So naturally when they come in the interface, there is every possibility the enzyme will undergo the deactivation. So this is how the different physical forces that affects the activity of the enzymes. The next, let me switch over to the effect of some kind of chemical parameters, and the first that is most important thing is the effect of pH. The pH plays a very important role in the biochemical reaction and enzymatic reaction. Now question comes, why? The reason is that enzymes have the ionic group on their active site. Am I right? Their ionic group, and variation of pH resulted them the ionic group. Like what is the ionic group? Maybe it is positive, maybe negative, maybe neutral. Now suppose active site we have positive. Now substrate is negative. So what will happen? Your substrate can freely interact with the active site and give the product. Now if the charge of the substrate and the active site is same, then there should be repulsion, and due to repulsion the activity will be very less. So that is why, that is how this pH works. And effect of activity, and it affects the activity and rate of reaction and alter the 3-dimensional shape. If the substrate contains ionic group, the pH affects the affinity of the substrate to the enzyme, and many enzymes inactivated outside this range 5 to 7. This is the range. Now here let me point out that we have come across different type of enzymes, like I have given the example of pepsin, salivary amylase and alkaline phosphatase. Now due to the these different enzymes had different optimum pH for their maximum activity, and pepsin is kind of enzyme that present in our stomach. Am I right? And we know our stomach pH is around 2. So at 2, this pepsin is kind of proteolytic enzyme. So this active as pH 2. Salivary enzyme amylase, that is even in our saliva, and that activity is more or less close to the neutral pH. That is now alkaline phosphatase, usually that occurs at the alkaline pH. This justify how that different enzymes are activated at different pH due to the different ionization characteristics of the enzymes. Now this is we want to go a little bit details on that how the pH effect on the enzymatic reaction can be explained. Let us assume this is the enzymes, which is inactive. This is inactive. Am I right? And this is also inactive. Now this is, let us assume this is active. So what is happening, that when the enzyme take out one hydrogen ion, then E minus 1 is there, and this is we consider as active. But if you take further one hydrogen ion, then E minus 2, it is becoming inactive. So you have the effect of hydrogen ion on the enzymatic activity can be explained very easily like this. Then when we remove one hydrogen ion, then it is active, but when you remove another hydrogen ion, it is become. So this is the optimum. This is the thing. Now we have used one term called y minus 1. Y minus 1 is the fraction of the y1 in E0. What is E0? Is the total enzyme concentration. And how you can explain this E0 in this particular E0, I can write this is equal to E plus E minus 1 plus E minus 2. This is how total activity of the enzyme can be. Now, we know that we have seen the velocity of reaction, maximum velocity of reaction is proportional to E0. Now, that when we consider E0, that means that whole enzyme that is active. But now, when you use this kind of strategy, then we find out only E minus 1 that is active. That means y minus 1, this fraction of the E0 that is active. So now the Vmax I can write this is equal to y minus 1 into E0, and that this is the enzyme that will proportional with the Vmax. This is how we can explain, how we can express the hydrogen ion, how it can affect the enzymatic activity. Now let us walk little bit in details. Now when you consider this first, let us assume this is reversible and this is also reversible, and equilibrium constant for this first step is K1 and equilibrium constant for the second step is K2. Now what is the K1? This is equal to because this is like this, this is like this, E minus 1 plus hydrogen ion concentration. Am I right? So naturally K equilibrium constant, this is K1, I can write this is K1, I think we could not write it, that K1 equal to hydrogen ion concentration, this product concentration, and E minus 1 concentration divided by E concentration. So we can write it very easily. Then we can take log here. What is pK1? pK1 equal to minus log K1. This is minus log. P stands for minus log. So this if we take the log, we can write this like this. Okay, that this we can write in this form. Now next is that in the second step that we have, so pK1 equal to this, again we can write pK1 equal to now if you look at before that, now here we have seen pK1 equal to this like this. So this we have done that. So we can write that now we can write that pK1 equal to minus log hydrogen ion. If we assume that E equal to E minus 1. If we assume that, then that is with log 1, that means log 1 equal to 0, and then we can write pK1 equal to minus, then this is equal to pH. And similarly, in the second step that we have, what is the second step we have? E minus 1 is plus minus, this is equal to E minus 2 plus hydrogen ion. Am I right? So we can write here that hydrogen ion concentration E minus 2 is the E minus 1, this is 1 will be there, equal to K2. So this is K2. So this is equilibrium constant. E0 I told you, this is any point of time equal to E plus E minus 1 plus E minus 2. So y minus 1, the fraction of enzyme that is active enzyme, that you can write E minus 1 divided by E plus this, and this is equal to 1 plus hydrogen ion concentration divided by K1 and K2 by hydrogen ion concentration. So, we can have a correlation between Y minus 1, how it is affected with respect to the hydrogen ion concentration. This is the final equation that we have, and then now here I forgot to explain that effect of pH on y minus 1. This will, as the pH changes, we find in this range your enzymes are active. This is the range that is active. So, so optimum pH will be in between this pK1 to pK2. And this is pH optimum, is the hydrogen ion optimum is the root over K1 into K2, and so pH optimum will be equal to half into pK1 by pK2. This we can easily find out that. So, therefore, now finally what we can write, I told you that Vmax, this already I explained you, that Vmax equal to what? K into E0, that we have done in before. Now, E0, all E0 is not active. So, this will be multiplied by E minus 1 is the fraction factor. So, this is exactly what we have written here, and then we put the value of y minus 1 here. Then we can find a correlation how the Vmax depends on the hydrogen ion concentration. So, we can, this is how hydrogen ion affects the value of Vmax. But now question comes, in the enzymatic reaction there is another constant called Km. What does it, Km signifies? Signifies the affinity of enzymes towards the substrate, or substrate affinity towards the enzyme. Now, if the substrate doesn't have different ionization strength, the state with different affinity of the free enzyme, then we can assume the Km is constant, insignificant. So, this is how we can explain the effect of pH on the enzymatic reaction. Now, here we have given, we summarize in this that how the different factors affect the enzymatic activities. Now, here we have seen the heat that affects the hydrogen bond and the highly disordered conformational change that take place. Now, cold also hydrophobic solvenation and aggregation of the organism, that the compound will take place. Mechanical force, this is highly disordered conformation. Radiation, functional group like peptides and highly disordered conformation. So, this table give you some idea that how different factors, different parameters influence the activity of the enzymes. Now, last of all, I want to discuss one very interesting topic, what we call enzyme stabilization. Now, what do you mean by enzyme stabilization? The major drawback when we go for any kind of utilizing any kind of enzyme is that the stability of the enzyme. Why? Because the enzyme we cannot use for longer period of time. We know that in the day-to-day life we use the battery. The battery has two types of life. One is called shelf life, another we call operating life. The same thing is applicable to the enzyme also. Enzymes, if you use for longer period of time, automatically the activity will be lost. And enzymes, even you keep it in the freeze for longer period of time, the activity of the loss. Now, now question comes, what parameters determine the enzyme stability? And the parameter that is find out the enzyme stability, that is called half-life of the enzyme. Now, what do you mean by half-life of the enzyme? The time required, the half of the activity of the enzyme will be lost. That is called half-life of the enzyme. So, here we try to point out here the enzyme stability, the extent to which the enzyme retain the structural conformation and its activity. Frequency depends on the half-life, and half-life is the time required the half of the activity of the to be lost as a result of deactivation and energy. So, here suppose this is the 100% activity and this is the time. So, this is the 50% activity. So, here that whatever time is there, this we considered as a that half-life of the enzyme, and this can be expressed T2 equal to ln2 by Kd. We have already given you that mathematical expression before that. If you use that, we can find out this equation. Now, here another question comes, what should be the strategy to increase the stability of the enzyme? There are three different strategies we have. One is by adding the stabilizing compound. This is the adding stabilizing compound to the storage or reaction. Example is the glucose galactosidase. Addition of 5 to 10% ethanol and 2 propanol increase the heat stability. Lactate dehydrogenase, addition of substrate lactate or effect of the fructose diphosphate greater thermostability. Alpha amylase, addition 50% of sorbitol, 70% sorbitol or calcium ion, the better storage and thermal stability. Chymotrypsin, addition of 50 to 90% glycerol improve the resistance to proteolysis. This is how different chemicals that influence the stability of the enzymes. Another important thing is that the chemical the modification of the soluble protein, because the enzymes, we know that enzymes, I told you the most of the part of the enzymes is inactive. So, this is the inactive, am I right? This is the inactive and this is active. So, this is very small fraction of the enzyme. Now, suppose the close to this if the some polyalanine group is there. So, there it has been observed that if you put some kind of polyalanine modified this active site, it will make some kind of stability of the active sites. Another way we can do, that is the immobilization of the protein or within the insoluble solid matrix. As for example, I can give you the example. Suppose this is the solid matrix and this is solid matrix, and inside the solid matrix if you have the enzymes. So, this is protected from outer this environment. So, suppose the immobilized you have put the enzymes in the some kind of envelope. So, it has some kind of protection inside this, and through which we can increase the stability of the enzyme. I can give another example is here is a cross linking, that is cross linking with papain that is available in the papaya, how it increases the activity by cross linking. What is cross linking? Suppose this is the enzyme and we have this glutyraldehyde, this is a cross linking agent, and this binds here and this binds here, and this is how they cross link with each other. Now inside if you put some kind of solid matrix, this embedded on the surface of the solid matrix and how the immobilization take place. So, this is the different way how we can stabilize the enzyme. So, in conclusion, I want to tell that this particular lecture deals with that effect of physicochemical parameters on the enzymatic activity. Initially, I tried to explain how temperature, fluid force and the surface tension affect the enzymatic activity, and then how the chemically that activity of the enzyme can be affected with respect to pH. And we have seen, we have determined the correlation between maximum velocity of reaction with respect to hydrogen ion concentration. Also, we find that Km value is more or less it is remain constant if the ionization characteristics of the active site between the substrate enzyme remain same. And finally, I discussed how the stability of the enzyme can be improved and how you can express the stability of the enzyme with the help of half-life of the enzyme. Thank you very much.